Here's one that we talked about at the very beginning of the unit, just very briefly. Diffraction. This was a property of waves. We said at the beginning of the unit that light undergoes diffraction, so therefore there's evidence to support the wave nature of light. What is diffraction? Remember from physics 20, diffraction is the spreading out of a wave. When a wave goes through an opening, it spreads out. And I found this picture on Google Images, thought it was the perfect picture to show diffraction, real diffraction, not just a hand-drawn thing that I can do on the board, but real diffraction of water waves. Here we've got our water waves going this way from out in the harbor or out in the ocean, and then it goes through this little opening here. You can see what happens to those water waves. The water waves spread out. They diffract. Refraction is the bending of a wave. Diffraction is the spreading out of a wave around a barrier or through an opening. We said that that's a property of waves, but that light undergoes diffraction, so therefore there's evidence to support the wave nature of light. Now, interference can occur when two waves, including two light waves, encounter each other. What does that have to do with diffraction? Well, if we have diffraction from two openings, like this, then we're going to have interference from both of those diffraction patterns. You can see on the left-hand opening here, we have a diffraction pattern that is more or less circular. And from the right-hand opening, we have a diffraction pattern that, again, is more or less circular. What I want to do right now is trace over some of these lines. I'm going to trace over my crests in green. So my crests will be green. My troughs of the waves will be blue. Let's make this a crest. Well, if that's a crest, then the next crest will be right here. The next one will be right here. Right here. We go to the next one, the other opening. The waves produced by the second opening are going to produce crests and troughs as well. Here's my first crest. Okay, my second crest. And so on. Every second one is a crest. To save ourselves the bother of tracing through those again, we're going to say our troughs are black. So what's left there are my troughs. Green is crest, black is trough. Now we've got a whole bunch of crests and troughs going everywhere, producing this mishmash of waves, right? What's the interference pattern going to look like? What's it going to look like when a crest hits a crest and a trough hits a trough? Well, you guys know from physics 20, when a crest hits a crest, we get a certain kind of interference. It's called constructive interference. Constructive interference means we get a bigger crest. Or if a trough meets a trough, we also get constructive interference. That means we get a bigger trough. So bottom line is when we get constructive interference, we get a bigger wave. If it's a result of two crests, it's a bigger crest. If it's a result of two troughs, then it's a bigger trough. What I want to do right now is identify in red the areas where we get constructive interference taking place. Okay, where do we get constructive interference taking place? Well, we get constructive interference taking place where a crest meets a crest or a trough meets a trough. So everywhere where we see a line, two green lines coming together, we're going to put a little red dot. Everywhere we see two black lines coming together, we're going to put a little red dot, because that's going to represent areas where we get constructive interference. There's constructive, there's constructive, there's constructive. Okay, here's constructive. Okay, again, everywhere where we get two black lines, two troughs, or two crests coming together, that's where we're putting the little red dot. I wouldn't panic about drawing this, guys. Okay, it's not the end of the world. I just want you to be able to see this. Okay. Now let's put a little blue dot everywhere we have destructive interference. In other words, where a crest meets a trough. Where a crest meets a trough, that means we cancel them out, right? You get nothing. So let's draw those areas of destructive interference in blue, where green meets black. should start seeing some patterns here. If we start joining these lines together, then we get these lines of destructive interference, and we also get these lines of constructive interference. The areas of destructive interference, that's where a crest met a trough, we call nodal lines. The areas of constructive interference, where a crest meets a crest or a trough meets a trough, and we get either a bigger crest or a bigger trough, we call constructive interference. And we call them antinodal lines. Now, if these are water waves, like it was in the picture that I showed you just a second ago, then when we're looking at them from above, we will see clear, distinct lines of constructive and destructive interference. We will see on the blue lines calm, smooth water. We will see on the red lines alternating areas of really big crests and really big troughs. Okay, if you happen to be laying on an air mattress trying to read a book on a blue line, you're going to be very comfortable reading that book, because you're just going to be sitting there on this calm, smooth water on this blue line, area of destructive interference. But if you're trying to read a book on an air mattress on one of these red lines, these antinodal lines, or these lines of constructive interference, then you're going to be bobbing up and down like crazy, because we've got really big crests and really big troughs. So you're going to be going up and down like this, as opposed to just lying there nicely on the blue line. If that's a water wave, that's what it's going to be. Now, if these are light waves, we're not going to see this. We're not going to see the areas of constructive and destructive interference here. Okay, light has to bounce off of something in order to see it. So we're not going to see big, bright lines right here and dark things right here. The way we detect constructive and destructive interference lines, or antinodal and nodal lines with light, is to put a screen over here. Let's put a screen over there, like a piece of paper or a piece of cardboard or a wall or something that will reflect the light. If we do that, then we're going to see on that screen alternating areas of bright spots and dark spots. We're going to see a bright spot right here. That was where we had constructive interference. We're going to see a bright spot right here. Again, constructive interference, a bright spot right here, where constructive interference took place, a bright spot. A bright spot. In between, what are we going to see? No light. We'll call it a dark spot because there's no light there. There was destructive interference. So the interference pattern that's produced on this screen as a result of this diffraction and then interference of both the diffraction lines looks like a series of bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. Does that make sense? Now, if we take a look at that series of bright spots and dark spots again on that screen, like we showed you on the last page, it looks something like this. Right? Bright spot, dark spot where there was no light. Bright spot, constructive interference, dark spot where there was no light, destructive interference. If we plot a graph of the intensity of that light versus the position, so in other words, the position x along the x-axis here, the intensity, how bright the light is, then it would look something like this. Now, this is the best I could do with Microsoft Word, but really we should have kind of curves on the top there. It should be a little bit smoother. You can see that the middle line, the middle bright spot, is the brightest bright spot. And then as we go out from there, it becomes a little bit less bright. Okay, the intensity is a little bit less. Okay, the intensity is a little bit less. What do we see in between here? There's no bright spot, right? It's a dark spot. There's no light there. So what's the intensity right here? Or right here, or right here? the intensity is 0. So this is what you physically see. This is a graph of what you see. Intensity of what you actually see, intensity of the bright spots and the dark spots versus the position of those bright spots and dark spots. So this bright spot would have an intensity that was really, really high. This bright spot would have an intensity that's a little bit lower. This bright spot would have an intensity that's a little bit lower. That middle bright spot, that brightest bright spot, that central bright spot, we're going to call our central maximum. Our central maximum, because it's a maximum area of light. It's a bright spot. I'm going to label it with the number 0. The next bright spot to the right and to the left of it we'll call the first order maximum. We're going to label that with the number 1. Whoops. Say number 1 and then I'll write number 2. We're going to label them both with the number 1. The second order maximum, we're going to label with the number 2. The third order maximum, the fourth order maximum, the fifth order maximum, and so on and so on and so on. I just haven't drawn any more than second order maximum. The first order minimum, that's a dark spot, destructive interference, a nodal line. First order minimum on the other side. Second order minimum on the other side. We're going to make this 0.5. We're going to make this 1.5. Now what I'm doing here is a little bit different than what you're going to see in a lot of books. Not all of them. Some of them use the system that I'm using here, but a lot of books use a slightly different system. But I think this way is better. I think this way makes it a lot easier for us to solve the problems that we have to solve. So if you ever see something a little bit different, if you ever see it labeled a little bit differently, that's okay. Doesn't mean they're wrong, doesn't mean I'm wrong. Okay, as long as you can both arrive at the same answer, then they're both right. So my first order maximum will be, we're going to say 1. My second order maximum is going to be 2. My first order minimum is going to be 0.5. My second order minimum is going to be 1.5. In other words, my minimums are going to be whatever the number is minus 0.5. My third order minimum would be 2.5. My 16th order minimum would be 15.5. My 17th order maximum would be 17. Does that make sense? So my maximum is the number. My minimum is, we're going to subtract 0.5 from it. I do that now. What a lot of sources, a lot of books do is do that in the equation. They have a couple of different equations for minimum and maximum. We use one equation that works for both minimums and maximums, and we just have slightly different numbers to accommodate for that. Now, there are a couple of equations that we're going to use to describe this. Two equations you see up on the board here right now. I'm going to redraw this so that we can label some of these variables, because most of these variables are going to seem kind of foreign to you right now. Here's my two openings. Okay, those two openings both diffract the light. Those diffraction patterns take place, those circles take place, right? Produce an interference pattern that on the screen up here produces a bright spot, and a dark spot, and a bright spot, and a dark spot, and so on. This is my central maximum that we called 0. This is my first maximum that we called 1, and 2, and 3, and 4, and 1, and 2, and 3, and 4. And of course the minimums, 0.5, 1.5, 2.5, 3.5, and so on, and so on, and so on. Let's try to figure out what these variables mean here now. Lambda, that's the easy one, right? That's wavelength. That's the wavelength of the light, and it's going to be measured in meters. it's going through these two openings, diffracting and interfering. The wavelength in meters. And that's going to be the same thing in both of these equations. D is going to be the distance between the openings, the distance between the slits, from the center of one slit to the center of the other slit. And that's going to be measured in meters. Now, this is going to be a really, really small number. So this D is going to be, it's not like it's going to be 1 meter or 1.5 meters. It's going to be centimeters. It's going to be even smaller than that, millimeters even, smaller than that even. It's going to be a really, really small number. So don't be surprised if you see D as 10 to the minus whatever. D is the distance between the two openings. So we're good with D now. L, right here, is the distance from the screen to the openings. However far away the screen is from those two openings that caused the diffraction and interference. I labeled it as a capital L there. In the equation, it's actually a lowercase l. I just can't do a handwritten lowercase l to not look like a 1. X, here's where it starts becoming a little bit trickier. X is also a distance. It's a little bit confusing here because D is a distance, L is a distance, and X is a distance. X is the confusing distance, though. X could be the distance between the fourth order maximum and the first order maximum, or it could be the distance between the third order maximum and the first order minimum, or it could be the distance between the central maximum and the second order minimum. X can be any distance you want, from any maximum to any other maximum or any other minimum, or any minimum to any other max or min. It can be anything you want. Well, how does that work? We'll talk about that in a second. We'll reconcile that in just a second, okay? X is the distance from any maximum or minimum to any other maximum or minimum. Sorry? They'll probably give you X, yeah. So you're probably going to use the one that you were given. Okay? It doesn't really matter which one it is. From 1 to 4, from 0.5 to 3, from 0 to 2.5, doesn't really matter which one it is that you're given. But you got to understand that we're going to get a different number for lambda, right, if we have a different number for X. So how does that work? Well, the key is we can use whatever X we want as long as N is consistent with it. N is the difference between the maxima or minimum number. So for this one, we would say that N is equal to 3, because 4 minus 1 is equal to 3. For this one, we would say that N is equal to 2.5, because 3 minus 0.5 is 2.5. For this one, we'd say that N is equal to what? What's N equal to over here? 0 to the third order minimum, N would be equal to 2.5. 2.5 minus 0 is 2.5. So X can be whatever you want, but N has to be consistent with X. Does that make sense? That's why we labeled all these 1, 2, 3, 4, 5, or 0.5, 1.5, 2.5, 3.5, so we could start subtracting the maximums and minimums here. 4 minus 1, 3 minus 0.5, 2.5 minus 0, so on. Not much left here. Theta is an angle, but it's always got to be measured from the central maximum. It can be the angle from the central maximum to the first order maximum. It can be from the central maximum to the third order minimum. Just 2 seconds here, guys, and then we'll finish up. To the third order minimum. It can be whatever angle you want as long as it's measured from the central max. X can be measured from anything to anything. It doesn't have to be from the central maximum, anything to anything. Theta can be anything almost, but it's got to be measured from the central maximum. But n has got to be consistent with it. What would n be in this case? 1 minus 0 is 1. What would n be in this case? What is it? 3.5. Does that make sense? If we're good with those two equations and what those variables mean, then I want to point out one more little thing. The second equation is starred. It's starred because it's not actually true. It's not actually, strictly speaking, correct. It's an approximation, but it's an approximation that works very well at small angles. It's an approximation that works very well in 95% of our problems. I will tell you in a little while when it doesn't work so well. For now, we'll just go with it. Okay, assume that it works. Okay, but keep in mind that it is an approximation. It doesn't take into account the value of the angle, and that actually does matter. But it's going to work for 95% of our problems. You'll see when it doesn't work when the time comes. This equation right here, the one with theta, the one with the angle, will always work no matter what. You got that? So if in doubt, go with this one. If in doubt, go with this one. But 95% of the time, this one's going to work as well. When it doesn't work, I'll point that out so that you know when it doesn't work. All right, let's take a look at an example here. Monochromatic light. What does that mean, monochromatic light? What does one what? One color. Mono means one, chromatic means color, so one color light. The reason we're talking about monochromatic light here is because if we were talking about multiple colors, look, you can see take a look at these equations again for a second. You can see if the wavelength of the light is different, then the angle is going to be different. So what's going to happen here is if we have a rainbow of light or white light going through here instead of just one color, we're going to get all these bright spots, but we're going to get bright spots of different color. We're going to get red bright spots. We're going to get blue bright spots. We're going to get yellow, red, orange, yellow, green, blue, indigo, and violet bright spots. And they're all going to be in different places. How do we know where they're going to be? Well, we end up getting a spectrum. Okay, we end up getting, in the middle, the central bright spot, we end up getting all of the colors, essentially white light. If it's multiple colors that are going through there. If it's only red light or monochromatic light going through there, we get one bright spot and it's going to be that color. But if we have white light going through those two openings, we're going to have white light right there. But we're not going to have white light right here. Because when we're at an angle, when lambda is different, the angle is going to be different, making the light split up just like it does in a prism. The only difference here is in a prism, it splits up into red, orange, yellow, green, blue, indigo, and violet. Okay, here it splits up the opposite. So we would see violet. It's like saying the alphabet backwards. I can't do that. Roy G. Biv. Let me write it out. We would see violet, indigo, blue, green, yellow. I can't even say it very fast when I'm reading it backwards here. Green, yellow, orange, and red. Okay, same thing right here, same thing right here, same thing right here, same thing right here. That's a little bit harder to deal with because we're seeing all these different spectra. We're going to see a rainbow here, 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 and a rainbow here, and so on. Okay. In the first question we're dealing with there, they're telling us that it's monochromatic light so that we're not seeing all those colors. All we're seeing is exactly what I showed you when we were going through this. A single red bright spot or a single whatever bright spot, okay, here. And then another single bright spot here. And then another single bright spot there. Does that make sense? Is that kind of clear what's going on here? Okay, the vast majority of time, it will be monochromatic light. If it's not monochromatic light, if it's multicolored light, then what I want you to do is pick a color and go with it. So if it's not monochromatic light, pretend that it is. Pick red and go with red. Or pick blue and go with blue. But never use all of them in the problem. Just pick a color. Does that make sense? Pretend that it's monochromatic light if it's not. If you've got data about yellow, then go with yellow. If you've got data about red, then go with red. Pretend that it's monochromatic light. They're separated by 0.30 millimeters. I'm going to circle that. The first bright fringe, that's going to be a maximum, is located at 0.080 degrees from the central antinode, the central bright spot. This is going to be theta. Okay, this is going to be, what's this one going to be? 0.30 millimeters. That's going to be a little d. Okay, what's n going to be? They tell me n is equal to 1 here. I don't like them saying that, n is equal to 1. It is actually equal to 1. But I don't like them saying n is equal to 1, because what they're saying is, you know, look, we labeled this as 1, 2, 3. I don't like them saying n is 1, 2, 3, because n is the difference in the maxima, not the actual maximum number. Does that make sense? So if we were going from 1 to 3, we wouldn't say n is equal to 1 and n is equal to 3. We would say n is equal to 2. That make sense? They're kind of saying here, n is equal to 1, n is equal to 3. I just don't like the way they're saying that, that's all. Okay, so you ever see that? Don't pay any attention to that. Okay, just look at the fact that it says, okay, look, it's the first antinode, the first bright spot. If we're dealing with the central and the first, then 1 minus 0 is equal to 1. That make sense? All right, so n is equal to 1. We're looking for the wavelength of the light here. We got a couple equations here. Lambda is equal to d sine theta over n. Lambda is equal to xd over n times L. Which one do you want to use? Let's use the first one, right? Clearly, we're going to use the first one in this case. Oops. So I write down the second one. Perfect. It's a good thing we have period 3 and period 4 to record, since I'm making these mistakes here. D sine theta over n. D is, we're going to convert that to meters, so it's going to be 0.30 times 10 to the minus 3. You can actually leave this in millimeters, but if you do, you're going to get a wavelength in millimeters, right? I don't want to do that, because the reality is, on a test, you're not going to get millimeters as one of your options. Okay, it might be meters, it might be nanometers, it's not going to be millimeters. The easiest thing is go to meters, and then you can work from there. So 0.30 times 10 to the minus 3 times sine 0.080 degrees. That's a really small angle, but that's not uncommon. N is equal to 1. We do that calculation. Okay, we can do that. What do we end up getting there? .397 times 10 to the negative 5. Yeah, I don't think that's right. I'm going to guess it's going to be 10 to the minus 7 meters. 4 point what? 4.2 times 10 to the minus 7. Now, I didn't know the answer to this question, but why did I guess that you were wrong when you said 10 to the minus 5? Why did I guess that it should be 10 to the minus 7? In these problems, we're almost always going to be dealing with, no? Okay, never mind. Visible light. Visible light is in that range of 10 to the minus 7. Now, I didn't ask you to memorize the wavelength of visible light. I asked you to memorize the frequency range. But if you calculated the wavelength range from the frequency range, you would find that visible light is in that 10 to the minus 7 range. So, listen, it's not, you're not guaranteed of having the wrong answer by getting 10 to the minus 5. It could be ultraviolet that you're using here, but it's almost certainly going to be visible light. Be careful there. And the mistake that she made was that she was in radian mode, right? You know what? That's a really easy mistake to make, especially when you see an angle that's that small, right? Because it kind of just makes it look radian almost when you see a number that's that small. (691) 13.9 says a student measuring the wavelength of light emitted by krypton gas directs light through two slits separated by 0.264 millimeters. We're going to circle that again because we don't want to see millimeters, we want to see meters. That's going to be D. This is going to be L. the distance between the second bright fringe and the central antinode. Now they're saying n is equal to 2 there, but we're just going to say it's the second antinode in the central bright spot. In other words, the second bright spot and the central bright spot. N will be equal to 2, but only because it's 2 minus 0. L is 3.0, yeah. This is going to be x, but we don't want centimeters again, we want meters. We're looking for the wavelength here. In this case, we're probably going to say lambda is equal to xd over n times L, right? xd over n times L. X is going to be 1.18 times 10 to the minus 2. D is going to be 0.264 times 10 to the minus 3. N is going to be 2. And L is going to be, what is L? 3.0 meters. I want us to take a look at the value of X and L here for a second. Is L more than 10 times bigger than X? Is L more than 10 times bigger than X? Yes, so you're allowed to use this equation. Okay? Yes. If L is more than 10 times bigger than X, we can use that equation. Now, strictly speaking, that's not the rule. The rule has to do with the value of the angle. If the angle is bigger than a certain value, then we're allowed to use it. Sorry, is smaller than a certain value, then we're allowed to use that equation. Having said that, though, we don't know what the angle is here. So I've just kind of looked at a rough look at it. You know, we don't need to find the angle. We're going to say, look, if L is bigger than 10 times X, then we can use this. The reality is we could actually go a little bit further than that, but 10 is a nice round number. 10, we're erring on the side of caution by using the number 10. If L is 10 times greater than X, we can use this equation. And it will be more than 10 times greater than X almost always. Check it each time you see that you want to use this equation just to make sure. If it isn't, well, then you're going to have to actually calculate the angle. You're going to calculate the angle. We know what X is. We know what L is. We can calculate the angle, and then we can go use the other equation. But that's a bit of a pain in the butt, right? So if you can use this by recognizing that L is more than 10 times greater than X, then let's just do that. What's the value of lambda work out to be? I'm not sure, but I'm going to guess it's 10 to the minus 7 meters. 5.2 times 10 to the minus 7. Okay, which again tells us that it's in that range of visible light. You're almost always going to get 10 to the minus 7 meters here. Again, don't panic if you don't, but I would double check it if you don't. Good? All right, you have 2 sets of homework tonight over the weekend. You have the practice problems on page 689, and you have the practice problems on page 691. They both involve those 2 equations that we learned. Neither set of them should be incredibly difficult. Just pay attention. I'll caution you on this. Pay attention to whether you're dealing with maxima or minima. There's 1 or 2 questions in there that they're going to try to trick you. N is not going to be 2 or 3 or 4. N is going to be 2.5 or 1.5 or 4.5. Okay, so pay attention to that, whether you're dealing with maxima or minima, so that you can make N the correct value. And finally, make sure, if you're going to use this equation right here, make sure that L is more than 10 times the value of X. Okay, I think it will be for all of them, but make sure that it is. Okay, let's try one more. A diffraction grating has 1,000 lines per centimeter. 1,000 lines, what does that mean? Light passes through the diffraction grating. An interference pattern is produced on a screen 4 meters away. The first order bright fringe is 19.2 centimeters from the central antinode. What's the wavelength and the color of the light? What does that mean? Well, the problems that we've dealt with so far in the last two examples have dealt with two openings. Here's an opening, here's an opening. Okay, that's what we call a double slit experiment. This was first performed by a guy named Thomas Young, the Young's double slit experiment. Two slits, double slit, right? The same analysis applies, however, if you have more than two slits. Maybe you've got, how many is that? 6 slits. Or maybe you've got a whole bunch more openings for the light to go through. Or maybe you've got 1,000 of those lines every centimeter. Not 2 of them or 4 of them, but 1,000 of them in a single centimeter of distance. So that's not D. It's telling me how many lines or how many openings we have per centimeter, not how many centimeters per lines. It's not D. We'll deal with that in a second, okay? We know what this is. This is L. Okay, the first order bright fringe is 19.2 centimeters away from the central bright spot. That's going to be X, but we're going to make sure we convert that to meters. N in this case, first order bright fringe, central bright fringe, N is going to be equal to 1. We're looking for the wavelength, and we won't worry so much about the color. But we got to figure out that 1,000 lines per centimeter. We know what it means, but how do we put it into an equation? Well, if I have 2 openings in a distance between those openings of 3 times 10 to the minus 5 meters, then that's not the number of openings or lines per meter, it's the number of meters per line. If I've got lines per meter instead of meters per line, it doesn't represent D, it represents 1 over D. So if you ever see that, a diffraction grating with this many lines per meter or this many lines per centimeter, it's not D, it's 1 over D. Well, that makes it easier. Okay, we don't have to work very hard now because we just got to get D. If we've got 1 over D, how are we going to get D? What are we going to do? By what? Multiply the 1 over 1,000 times 1 is 1,000, right? It's going to be 1 over 1,000, yes. Take 1,000, flip it over, right? X to the minus 1, it gives me 1.0 times 10 to the minus 3. But what's that going to be? 1.0 times 10 to the minus 3, what units? Centimeters. If you have lines per centimeter, don't try to convert it to lines per meter. Leave it in lines per centimeter. Then get centimeters. So flip it over first, then convert it to meters. This would be 1.00 times 10 to the minus 5 meters. Okay, don't try to convert it to meters before you flip it over. Do the flip first. You can do it either way. But if you try converting it first, lines per meter as opposed to lines per centimeter, I can virtually guarantee you're going to move the decimal place the wrong way. The centimeters is on the bottom. Instead of dividing by 1,000, you would have to multiply. Sorry, instead of dividing by 100, you have to actually multiply by 100 there. Again, most of you are going to mess up on that. So get it into lines per, get it into centimeters first, and then do what we always do to convert centimeters to meters, and that's divide by 100. Okay, how does it go to xd over n times L? This is what we want to use, right? Can we use it? Is L more than 10 times the value of x? Yeah, it's about 200 times the value of x, right? X is 0.2, basically, 0.192. L is 4 meters. No, it's not 200, it's 20 times, right? 20 times. But it's still more than 10 times bigger than x, so this equation is perfectly valid. It's going to give us a really good number. X is 0.192. D, not 1 over 1,000, not 1,000, but rather 1.0 times 10 to the minus 5 in meters. N is going to be equal to 1, and L is going to be equal to 4 meters in this case. Let's pull out the calculator and see what we get for this one. Let's say 0.192 times 1 times 10 to the minus 5. And let's divide that by 4. We get 4.8 times 10 to the minus 7. You forget to flip over d, or 1 over d, I should say, or you forget to convert it to meters, or you convert it wrong to meters. Well, you're not going to end up with the 10 to the minus 7 there, right? We almost always end up with the 10 to the minus 7 there, so be aware of that, okay? Check that. If we don't end up with 10 to the minus 7, you should double check what you've done because you probably made a mistake. And in one of these questions, in all likelihood, it's right there that you've made the mistake. Dane? What color would that be? Okay. I'm not sure, to be honest off the top of my head. I'm guessing in that violet range again. But let's take a peek here. F is equal to V over lambda. Let's solve for the frequency. 3 times 10 to the 8 divided by 4.8 times 10 to the minus 7. What does that give me? 6.25 times 10 to the 14. Yeah, I don't think that would be violet. I think that's too low to be violet. I would say that's probably somewhere in that bluish, indigo-ish range, but I can't say for sure. I know that it's visible light, and I know that it's at the upper end of that visible light, you know, kind of above the green midway. Yeah, I'd say blue or indigo. Okay, green is halfway between 4 and 7.5, right? So this is going to be probably indigo, actually.